All right, let's talk about a paper with a title that sounds almost simple. Attention is all you need. But don't let that fool you. In 2017, a team from Google dropped this paper, and it didn't just make a splash. It basically created the ocean that modern AI swims in. It completely changed the game for language models. So we're going to break down what they did and why it was such a massive, revolutionary deal.
But to really get why this was so huge, we have to ask a pretty basic question, right? How does an AI actually understand a sentence? I mean, really understand it. The connections between words, the context, all the subtle stuff we do without even thinking.
Well, for a long, long time, the answer was pretty clunky. The go-to models, things like recurrent neural networks, or RNNs, they processed text one word at a time. Seriously, they'd read word number one, chew on it for a bit, try to remember what it meant, then move on to word number two. Imagine trying to read a whole book through a tiny keyhole. It works, but man, is it slow.
And that one-by-one approach, it wasn't just slow, it was a major bottleneck. The researchers called it the inherently sequential nature of the old models. And this wasn't just a small problem. It put a hard limit on how fast you could train these things. And maybe even more importantly, how well they could handle long, complicated sentences. So this whole sequential thing created two massive headaches. First, you just couldn't speed it up with modern hardware like GPUs. You were stuck in this one-at-a-time traffic jam, which made training take forever. And second, and this is a big one, by the time the model got to the end of a long sentence, it would often forget what happened at the beginning. It's that classic problem of long-range dependencies. The AI just couldn't hold on to context for very long. So, the Google researchers looked at this whole situation and decided to just throw it all out.
They proposed something completely different. An idea so radical, it got rid of the one thing everyone thought was absolutely essential for understanding language. And they spelled it out right there in the paper. They introduced a brand new architecture called the transformer, and it was based only on a mechanism called attention. That's it. No more sequential processing, no more recurrence. This wasn't just a little upgrade, it was a complete and total paradigm shift. They basically reframed the entire problem. Instead of that keyhole, they asked, what if a model could see the entire sentence all at once? What if it could figure out how important every single word is to every other word all at the same time? That single idea, seeing the whole picture, is the heart of the transformer. And the engine that makes this all possible? It's a powerful little concept called self-attention. Yep, this is the all-you-need part from the title. So here's the magic. When the model looks at a single word, let's say the word it, self-attention lets it scan the entire sentence to figure out what that it is referring to. Is it a dog, a car, an idea? Self-attention calculates a relevant score for every single other word in the sentence to find the answer. Okay, let's break this down with a library analogy, because it actually makes a ton of sense. The word you're focused on, that's your query. It's the topic you're searching for. Now the keys, think of those as the titles on the spine of every single book in the library. And the values, that's the actual content inside those books. So the attention mechanism takes your query, matches it against all the keys to find the most relevant book titles, and then pulls the content, the values, from those books. Simple, right? It's how it finds the best info. And this, right here, this is the math engine that makes that library search happen. It's called scaled dot product attention. Don't worry about the name too much. At its heart, it's just a bunch of math that compares your query to all the keys to see how similar they are. The results get fed through something called a softmax function, which is really just a neat way to turn those raw scores into nice, clean percentages that all add up to 100. And those percentages tell the model exactly how much of each value to pay attention to. It's a super efficient way to figure out what matters most. But wait, it gets even cooler. Why settle for just one librarian doing one search? The transformer uses something called multi-head attention. This is like having a whole team of librarians. In the original paper, it was 8 of them, all working at the same time, in parallel. Each head, or librarian, gets really good at looking for different things. Maybe one focuses on grammar, another on who did what to whom. By combining all these different perspectives, the model gets a way richer, deeper understanding of the sentence. Okay, so we've got this awesome self-attention block. Now let's see how the researchers put these blocks together to build the whole transformer. And there it is, the whole shebang. The architecture basically has 2 big parts. Over on the left, you've got the encoder. Think of it as the reader.
Its job is to read the input sentence and create a super rich understanding of it using all that self-attention magic. Then on the right, you've got the decoder, which is the writer. It takes that understanding from the encoder and, for something like translation, starts writing the new sentence out word by word.
But hold on a second. This creates a huge new problem, doesn't it? If you're looking at all the words at the same time, how do you know what order they're in? I mean, the dog bit the man is a very, very different story than the man bit the dog. If the model just sees a jumble of words, how on earth does it know the difference? See, the old RNNs didn't have this problem. They naturally understood word order because they read things one by one by one. But the transformer, in its brilliant move to go parallel and get super fast, tossed that advantage right out the window. Without a fix, it would just see a sentence as a bag of words with no clue about their sequence.
The solution they came up with is just elegant. It's called positional encodings. The idea is simple. Before you feed the words into the model, you add a little piece of information to each one that says where it is in the sentence. It's like giving each word its own unique GPS coordinate or timestamp. They used a really clever trick with sine and cosine waves to create these unique positional signatures. This little bit of math gets added right into the word's meaning, so the model knows not just what the word is, but also where it is.
So, with that final piece of the puzzle snapped into place, the stage was set for an absolute revolution. So why was this such a game changer? It really comes down to two huge wins. First, speed. Because you could process all the words at once, you could throw massive amounts of computing power at it. Training became blazingly fast compared to the old way. And second, context. Since any word could directly look at any other word, that whole long-range dependency problem, poof, gone. Information could jump from the start of a paragraph to the end in a single step. And the proof is in the pudding. The numbers don't lie. On a key machine translation test, the transformer didn't just do well, it smashed the previous records. And get this, it did it while using way, way less computational power than the other models. It was better, it was faster, and it was cheaper to train. That's the holy grail in research, right there. And this wasn't just some one-hit wonder for translation. This new architecture became the actual blueprint for pretty much all of modern AI.
You know that T in GPT, as in ChatGPT? Yeah, that stands for transformer. Models like BERT, T5, and the whole GPT family, they all come directly from this paper. This isn't just a history lesson. It's the DNA of the AI you're probably using every single day.
And it all circles back to that one powerful idea. The researchers dared to question a basic assumption that you had to read language one word at a time. And by doing that, they unlocked a completely new, vastly more powerful way for machines to understand us. Ultimately, what this paper showed us is that sometimes the biggest breakthroughs come from making things simpler, not more complicated. They took out what everyone thought was necessary and proved that really attention was all you needed. This single paper truly defined an era of AI, and it leaves you wondering, right? What's the next big assumption that's about to be completely overturned?